Assalamu alaikum. In this video, we're going to start with the explanation of equilibrium of a body, which is chapter 13 in the last unit of physics, equilibrium of a body. In this chapter, we have three main objectives we are going to talk about. The first one is the principle of interaction. The second one is equilibrium of a solid acted upon by two forces, and the third one is Hooke's law. Let's start with the principle of interaction. What do we mean by the principle of interaction? Let's take an example. If a body A exerts on body B a force Fa on B, this is body A, which is person, and this is body B, which is a box, for example. Body A exerts on body B a force Fa on B, then body B acts on A by a force Fb on A. Let's see. These are the two forces. The force exerted by A on B and the force exerted by B on A. This is the force. The blue one is the force exerted by A on B. The person is trying, or the man is trying to push the box by this force to the right, while the box also tries to oppose this force of the man by a force. We can say that the box exerts on the man a force Fb. So this force, the blue one, is force exerted by A on B, and the red force is the force exerted by B on A. What are the characteristics of these two forces? Let's go back first. The two forces here, as you can see, they are on the same line of action. We say that they have the same line of action, which is horizontally. And if you can measure them, or by magnitude, in forces in physics we talk about magnitude. In magnitude they are the same, they are equal in magnitude, but they are opposite in direction. So these two forces have the same line of action, the same magnitude, but opposite direction. Keep this in mind. These are the two forces represented here, Fa on B and Fb on A. The forces Fa on B and Fb on A are opposite, but they have, as we said, they have the same line of action and the same magnitude, but they are opposite in direction. So the relation between these two forces is force Fa on B equal to minus Fb on A. And the relation between the magnitudes of the forces is Fa on B equal Fb on A. So these two forces in magnitude, they are equal. We say that Fa on B equal Fb on A. But in directions, they are opposite. For example, a one towards the positive, the other should be towards the negative. This is why we say they are opposite. So we say vector Fa on B equal to minus vector Fb on A. This is the meaning that these two forces have the same line of action, the same magnitude, but opposite direction. Types of interaction. We have two types of interaction. As the two types of forces, we have two types of interaction. Interaction from a distance and interaction by contact. Interaction from a distance and interaction by contact. Interaction from a distance. Example: attraction or repulsion of magnets. Let's take these two magnets. These two magnets attract each other. The blue vector or the red arrow is the force exerted by B on A, and the blue arrow is the force exerted by A on B. Magnet A tries to attract magnet B. It exerts a force acting from a distance at the center of gravity of magnet B, which is here, and tries to attract it towards it. At the same time, magnet B tries to attract magnet A, and it exerts a force acting from a distance at the center of gravity of magnet A, which is here. So this force is FB on A, and this force is FA on B. They attract each other. Okay, FB on A and FA on B. Here we have repulsion. Magnet A tries to repel magnet B, and it exerts a force on the center of gravity on magnet B, which is here. At the same time, magnet B tries to repel magnet A, and it exerts a force at the center of gravity of magnet A. So this force should be FB on A, and this force should be FA on B. The same as here, they repel each other because we have SS. Okay? Name the forces of interaction between the magnets and represent them on the figure. Here we have first force, FA on B. FA on B is the force exerted by magnet A on magnet B. And FB on A is the force exerted by the magnet B on magnet A. This is FB on A, which is the force exerted by magnet B on magnet A. Write the relation between the magnitudes of these two forces. Between the magnitudes. In magnitudes, we don't have vectors. We don't put an arrow above the F, and they are equal in magnitude. Okay? In magnitude, they are equal, but in vectors, they are opposite. In magnitude, they are equal. Remember this, in magnitude, they are equal. In vectors, they are opposite. In vectors, vector FA on B, or force FA on B, equal to minus vector FB on A. In magnitudes, we don't have vectors. FA on B equal FB on A. For example, in magnitudes, we say they are both equal, for example, to 20 newtons. Okay? Both are equal to 20 newtons, for example. This is interaction from a distance. Let's take an example for interaction by contact. Consider a block B, which is this, suspended from a spring S, or string S, let's say string, which is a wire, for example, as shown in the adjacent figure. Name the forces of interaction between the box and the string and represent them on the figure. So what are the forces of interaction between the block and the string? First, Fs on B, the force exerted by the string on box. Force exerted by the string on box. If we don't know the name, here the name of this force is the tension of the string on box. If we don't know the name of this force, we say as here, we name it as here. Fs on B, force exerted by the string S on box B. And the other force is the force exerted by B on the string. Fb on S, force exerted by box B on the string S. Here, the force exerted by the string on S is the weight. Write the relation between the magnitudes of these two forces. So these two forces, let's represent them. This is the force exerted by the string on the box, and this is the force exerted by the box on the string. They have the same line of action, which is the vertical line. They have the same magnitude as we will see here, but opposite directions. So we say that Fa on B or F, here we have Fs on B equal to minus Fb on S, and in magnitude we say Fs on B equal Fb on S. In magnitude means this. In magnitude means this. In vectors, opposite directions, means this. Okay, this is about interaction. The second objective is equilibrium of a solid acted upon by two forces. Equilibrium of a solid acted upon by two forces. A solid S here, this is the blue one, is the solid S, is acted upon by a force F1 and force F2. Is at equilibrium, or means it is at rest. It is not moving. If the two forces F1 and F2 acting on this solid have the same line of action, the same magnitude, but opposite direction. Same line of action, the same magnitude, but opposite direction. So, solid S is in equilibrium under the action of two forces, F1 and F2, such that these two forces have the same line of action, same magnitude, but opposite directions. These two forces, F1 and F2, sets the body S to be in equilibrium. This allows us to write that F1 plus F2, since they have the same line of action, the same magnitude, but opposite directions, this allows us to write F1 vector plus F2 vector, or force F1 plus force F2 equals 0 vector. This means, what's the meaning of 0 vector? This means that this body S is not moving under the action of these two forces. If one of these two forces is greater than the other, then this body S should move. But here, since the two forces are the same in magnitude, the same line of action, but opposite directions, as if we are saying that they cancel each other, and the resultant of these two forces should be 0, no motion of S, and S is at equilibrium. This 0 means that the body S is at equilibrium and it is not moving under the action of these two forces. This is called the condition of equilibrium. The relation between the magnitudes of these two forces is F1 equal minus F2 as opposite in directions, opposite vectors, but in magnitude F1 equal F2. F1 equal F2. Another example of condition of equilibrium, consider a block S of mass M, 1.5 kilogram on a table as shown in the adjacent figure. This is the mass M on the table. The solid S is at equilibrium. The solid S is at equilibrium. It's not moving downward or not moving upward or left or right. Given gravity equal 10 Newton per kilogram. Name the forces acting on the block S. So who can tell? What are the forces acting on the block S? The block S is under the action of two forces. Its weight, how the force exerted by the earth on the block S, its weight, which is vertically downward, and the normal reaction of the table, which is vertically upward. Okay? Or weight, these are the two forces, weight of the box, forces acting at a distance, and here tell whether each force is acting from a distance or contact force. So we say weight of the box is the first force acting on the box, which is a force acting at a distance, and N, normal reaction of the table, N, which is a contact force. This is the normal reaction. This is N, the normal reaction of the table. It starts from the surface of contact between the table and the box, and the weight starts from the center of gravity of the box. Let me remind you we have said in the previous chapter that all forces acting from a distance, their point of application is the center of gravity of the receiver. The center of gravity of the receiver. And all forces or all contact forces, the point of application is the point of contact between the actor and the receiver. So here, N is a contact force. The point of application is the point of contact between the surface, this is the surface, and the box, which is, let's say, here, and it's the start of the red force, which is N, and weight is a force acting from a distance. Its point of application is the center of gravity of the box, which is the point G. Okay? Write the relation between the forces, or write the condition of equilibrium. So we say here that these two forces have the same line of action, which is vertical, same line of action, which is vertical, same magnitude, but opposite directions. So we say that at equilibrium, W plus N equal 0 vector. This is the condition of equilibrium. This is what the condition of equilibrium, or the relation between the forces, since they have the same line of action, opposite directions, but same magnitude. So we say that W force plus N force equal 0 vector. Determine the value of the magnet of each force. So here now we say that W force equal minus N force, and the magnitude is W equal N, as you will see here. First, we calculate the weight. Weight equal mass times gravity, which is 1.5 kilogram times 10 Newton per kilogram equal 1.5 Newton. And since we have W plus N equals 0 vector and N equal minus W, then in magnitude N equal W equal 1.5 Newton. Another example of the condition of equilibrium, tension in a string. Consider a block S of mass M equals 750 grams suspended from a spring R. This is the spring R ressort. As shown in the adjacent figure, the solid S is at equilibrium. This S is at equilibrium given G equal 10 Newton per kilogram. Name the forces acting on the block S. Tell whether each force is force acting at a distance or contact force. Represent them on the figure. Name the forces acting on the block S. So S is under the action of two forces, its weight and the tension. Let's start with the first one, weight. Weight of the box, which is a force acting at a distance, and tension force, which is a contact force. And let's represent them now. Weight is vertically downward starting from the center of gravity of S, and the tension is vertically upward starting from the point of contact between the spring and the solid S, and this is the tension. Write the relation between the magnitude of the forces. As we said here that the two forces at S is at equilibrium, so W plus T equals 0 vector. Condition of equilibrium. At equilibrium, W plus T equals 0 vector. Then W equal minus T. In magnitude, W equal T. Determine the value of the magnitude of each force. We say here that W equal T equal mass times gravity, but mass should be performed or transformed into kilogram, converted to kilogram. Mass equals 750 grams equals 750 over 1000 equals 0.75 kilograms. So we say now W equal T equal mass times gravity equals 0.75 kilogram times 10 Newton equals 7.5 Newton. Or أنقلتهم مع بعضهم, we can separate them. T equal W equal 7.5 Newton. That we said here, because we said here that weight equal T, the magnitude of the relation between the magnitude of the forces. So note, to describe the relation between magnitude, we start from we we start from the condition of equilibrium. We say that at equilibrium, for example, in this example, w vector plus t vector equals 0 vector, then w vector equal minus t vector, so w equal t. When we are asked to describe the relation between the magnitude of forces, we start from the condition of equilibrium, w vector equal minus t vector, so w equal t. Okay, this is enough for today, and I hope you will watch it well and understand it well, and I'm ready to answer your questions. Please watch it and study it well, and thank you.